let's start the next chapter of Software Foundations, lists.v. This chapter, as the name suggests, is mostly about lists, but it also contains some good other data types like options and pairs that we're going to cover too. So let's get started with that. We'll start with pairs of numbers. So you might be used to pairs from other languages that you've worked in. Many functional languages have pairs. Python has them. A more general notion than a pair is called a tuple. So any of these is the idea of taking a few different pieces of data and gluing them together. Let's see what that looks like with pairs of natural numbers. Here's a calc type nat_prod. So this is meant to be the product of natural numbers. Product here is in the sense of Cartesian product, taking two sets and combining them together such that you have one element from each set. That's the notion of Cartesian product in mathematics. Here what we're doing is constructing pairs of natural numbers. So we have one constructor for this inductive data type. That constructor is named pair, and it carries two pieces of data along with it, which are two natural numbers. So the only way to construct a nat_prod is with this pair constructor that we give two natural numbers to. Here's an example of a pair. We could have the pair containing the number 3 and the number 5. That is a nat_prod. We could then define functions to work with pairs. For example, here is the first function, or FST. There's some letters missing there, but this is the traditional name for this function. It's short, only 3 characters long. FST, first. What is the first component of a natural product, of a nat_prod, of a pair of natural numbers? Well, in order to extract the first component of it, we need to pattern match. That's how we've been dealing with any kind of value of an inductive type. So we pattern match that nat_prod that was passed in. There's only one possible constructor that could have been used, so we write a pattern match with just one branch there, which is a pair containing a value x and a value y, and then we'll return x, because that is the first component of that pair. So of course, the output type of that function is nat, because the first component of a nat_prod is, of course, a nat. We could also get the second component of a pair. So here's a function to do that, snd, second. So what does second do? It does essentially the same thing as first. It pattern matches against p. It looks to see for that pair constructor there, the two pieces of data carried along with it, x and y, and then the only difference is that second is going to return y, whereas first returned x. Now, I could actually clean up this code a little bit. For example, I never needed the pair or the name y inside of that pair constructor there. I'm not going to do anything with the second component carried along with that pair in my first function. Likewise, I could simplify the second function by using that joker, that wild card, so that I don't have to give a name to a piece of data that I'm never going to use. So those are the first and second functions. And we could use those to compute with pairs. For example, if we take our pair 3, 5 and ask what is the first component of it, of course that computes to 3. Now, if you're used to pairs from mathematics or even from other programming languages, this is kind of a verbose notation that we have for them so far. Like we're having to write PAIR. It's more typical to write round parentheses around components of pairs. Using Coq's syntactic notation features, we can do this. Now, we're not going to dig deeply into how to use these features, how to write your own syntactic notations here. I just want to illustrate that this is possible in Coq, and in fact, the standard library does this. So, if you wanted to write round parentheses instead of PAIR, you could say I've got a syntactic notation, which is going to be round parentheses around two terms, x and y, and anywhere that notation is seen, it should actually be understood as the application of the pair constructor to the two terms x and y. Now, you can use that inside of values that you're writing, inside of expressions that you're writing, and even inside of patterns that you're writing. So now I could write 3, 5 in round parentheses as a pair. I don't have to write the PAIR constructor, and I can take the first value of that and get 3, of course. And I could recode my first and second functions to use that round parentheses as the notation over here on the left-hand side of the pattern match. I could even simplify that again. I didn't need to give y a name there. All right, so that's my implementation of first now, and also my implementation of second, with that syntactic notation to make it more pleasant to read. If I wanted to give some other kinds of examples of this, we could swap the two components of a pair. So we could take in a nat prod, return a nat prod. What do? We pattern match against it. We just deconstruct it into two values, x and y, and then return the pair that is constructed with y comma x instead. Right. So this is entirely equivalent to writing it like this, as we would have before we had the notation. But it's more pleasant to read the round parenthesis form of it. Nonetheless, this is exactly how Coq is going to understand it, because we defined our syntactic notation to say it's the same as the pair constructor. So let's restore that to the way that it was. We could try to prove things about pairs as well. So here's one way to state a theorem about pairs. We'll see a second way of stating it in just a second. Suppose you took in two natural numbers and you constructed a pair out of them. That pair would be the same thing as if you created the same pair and then took the first component of it and then put that as the first component of a pair, right? Or take the same pair, take the second component of it, and make that the second component of a pair. Right, so in a way, what we're saying here is that there's a way in which first and second and the pair constructor interact in the right way. Okay. That's easy. It goes through just by reflexivity. There's just really simple computation going on, because what does first do? It takes the first component of that pair, so that's going to be n. What does second do? It takes the second component of that pair, which is m. So we've got n comma m when that computes, and that's the same thing by reflexivity as n comma m over here. On the other hand, if you stated the theorem in a less verbose way, something perhaps surprising happens. So suppose you said for all nat prods p, for all pairs p equals the first p comma the second of p. Now intuitively that makes sense, right? You can take that pair, you can take the first component of it, make it the first component of a new pair, take the second component of it, make it the second component of a new pair. You should have the same pair back as a result. But the Coq proof for that, if we start off just with simple, actually doesn't do anything. Like, it didn't simplify anything on this left-hand side, or sorry, right-hand side there of the universal quantifier. If I tried reflexivity, actually that fails. It says unable to unify first p, second p with p. In other words, Coq can't understand those as being equal terms. And it's not because I forgot something simple. Like, it's not because I forgot to do intros p here or something like that. Right? The simple still doesn't change it. The reflexivity still fails. So what's going on here? The issue is that p to Coq here, on the left-hand side of that equal sign, is a kind of opaque thing right now. It's kind of not able to look inside of it and say, oh yeah, I know how this was constructed. It could only have been constructed with the pair constructor, and therefore there's got to be a first component and a second component that I could extract. Okay, so simple and reflexivity are not strong enough to peek inside, as it were, that value of the type nat prod. Instead, what we can do, well, we'll have to get rid of this reflexivity here. What we can do is tell Coq I want to take apart that value p. I want to destruct it. And you'll remember we learned the destruct tactic already. The destruct tactic is a way of taking apart values of an inductive type. In a way, it's a kind of pattern match, as it were. Like, we're taking them apart exactly as we would with a match expression. It's just here we're using destruct in the proof script, whereas we use these match expressions up here when we were writing a function on them. There really is a close similarity between match and destruct here. We'll discover that a little later on in another chapter. So now, if I want to take apart that pair, I can destruct the pair. And remember, I supply what's called an intros pattern here, which you can think of as essentially being the names that would be showing up after the constructor of that type. Right, so when we defined nat prod up above, it had one constructor pair, which carried two pieces of data, two natural numbers. So here we're just giving the names that we want to use locally for the two natural numbers that we get when we deconstruct that pair. So I destruct p as nm, and watch what happens here in the goals window when I do that. Now P has gone away, I've taken it apart, and I've got N and M as the two pieces of data that were carried by it. And now everywhere that P was, it's being replaced by N comma M. In fact, it's being replaced by pair, P-A-I-R, N, M, but we have that syntactic notation, so it looks a little more beautiful. So we've got N comma M equals this big expression, and that's exactly, in fact, the theorem that we proved up above that was a little more verbose version of what we're trying to do right now. So this can actually simplify. If I run simple, then the right-hand side of that, first and second, will get simplified, and we'll get the right components out. And then, of course, those two pairs are equal by reflexivity. Okay, so that is our first example in this lists chapter of working with structured data. Here we worked with pairs, which have just two components. Of course, just two components is a kind of a miserable special case. In the end, we'd like to have lists which could be of unbounded length, and that's what we'll turn to next.